Hello, I'm Jânio Lima from Cefet Rio de Janeiro, and I will present to you the paper Online Event Detection for Sensor Data. The other authors of this paper was Professor Eduardo Ogasawara from Cefet Rio de Janeiro, Rebeca Salles, Luciana Escobar, Laís Baroni, and Professor Fábio Porto from LNCC. To introduce the problem, let's imagine the current scenario in organization, in smart home, and everywhere, where there are a lot of devices with sensors generating a large amount of data. In many situations, all this data in smart things is read by sensors and generating a continuous stream of data, for example, in the cloud. This chronologically organized data represents a time series. When we analyze stream time series in continuous flow, we can observe the occurrence of significant behavior changes. These behavior changes represents time series events. A time series event is a point or an interval in a time series with defined meaning in a domain area of knowledge. But when we are talking about online event detection, we face new challenges. First of all, we can get in trouble if we try to do things linearly, like this illustration. Actually, in online event detection, especially in sensor data, we need to do things differently. It's necessary to accomplish real-time data processing. That is, instead of collecting data and later analyzing it, we have algorithms running simultaneously with the monitored process, as these figures try to illustrate. The process running and the algorithms monitoring it and trying to detect events simultaneously. But to do that, we have the need of high performance computing and advanced machine learning techniques. Another challenge in this area is there is an absence of generally applicable methods. In this context, this work contributes by providing a taxonomy for online event detection in time series, including incremental and adaptive learning, and some of the main methods addressed in the literature. Before present our taxonomy, let's introduce some key concepts related with the background of our research. A time series, as illustrated in this figure, refers to observation collected over time, with the behavior studied as a function of its past data. And formally, a time series X is composed by the points x1, x2, x3, and so on to xn, and where the x1 is the oldest time point in the chart, and the xn is the newest point in the chart. Another important concept is the notion of stationarity and non-stationarity. The stationarity is a special situation in a time series that requires strict constraints such as constant mean, variance, and covariance. And most methods assume stationarity of the time series. But the problem is a time series X that violates any of those constraints is considered a non-stationary time series. As the main contribution of this work, this taxonomy related to the online event detection for sensor data is presented. As we can see in the figure, we have divided the taxonomy in 7 main categories. Further details will be presented below. Let's start with the types. We divided the types in trend anomaly, when events escapes from the trend in generating process, the volatility anomaly, when the events represents variations in data volatility, and the concept drift, when we are working with data that evolve or change over the time. The importance of the types of events or anomalies is because we have different approaches and different methods applied to different types. For example, to the trend anomaly, we have the moving average and the decomposition, and another types and its applications was presented on the paper. Then we have the granularity of the events. The punctual is when an individual instance data differs from the residual of the data. Contextual, we are talking about data instances that are anomalous in a specific context or condition, and because that it is also named as conditional granularity. We have then the collective, that is the situation where data instances that may not be anomalies by themselves, but their occurrence together as a collection is an anomaly. Then we discuss the modes of the methods learned, and it's so similar to the other machine learning modes. We divide it in the supervised and semi-supervised, when the methods learn with the labels, and unsupervised, when the methods learn without labels. Then we have the strategies. The most common is the model deviation, when we create and fit a model to the available data and use it to detect events in new data. The classification and clustering based analysis is when we treat the event detection has a problem of classification or clustering. And the statistical techniques use the distribution of the data to understand the time series and detect events. Continuous, we have the approaches we use it to learn. The approaches is divided in two. The static, when we have a model trained on large data samples and use it on new data on stream. And we have the dynamic, when the model just initialized on a data sample and then learn incrementally as a new data arrives in the stream. Then we have the tasks of the big data. The big data tasks is divided in data ingestion, that is the move data from a source to a destination, for example, to connect the on-premise systems, cloud repositories, and message hubs. Then we have the data storage that, especially in the big data scenario, we need high capacity, performance, fail safe, and the support to large data streams. And the data processing, that is the consume from the storage layer. And in some situation, we need parallel, distribute, and real-time processing. And finally, we have the methods that is divided in model driven, when we have more traditional and correlated with statistics, for example, the exponential weighted moving average and the other examples. And in this situation, we have smaller computational requirements. And we have the data driven, that is enabled by machine learning. For example, we have the neural net, the NNNet, the feed forward neural network, the CNN, and another algorithms. And in this situation, we have the advantage that is not necessarily restricted to certain kinds of problem. That is a common situation in the model-driven methods. As final remarks, we would like to focus on these 3 points. This paper featured a review of basic categories related to online event detection. Certainly, not all of the content has been exhausted, but our taxonomy can contribute a lot for researchers who wish to go deeper into specific aspects of the online event detection for sensor data. This presentation, as well as the paper, reinforce that there is no definitive general method for the online event detection tasks. And researchers in the area must pay attention to the need of an adequate event detection balance between accuracy and performance. Finally, the authors would like to thank CNPq, CAPES, Petrobras, and FAPERJ for partially funding this research, and present the references used in the research.